Observe the exhaust plume of this rocket engine during sea-level ignition. The plume structure is dynamic, shifting in shape as the vehicle ascends through layers of varying atmospheric pressure. The combustion process generates high-pressure gas, but the physical geometry of the engine bell is what converts that thermal energy into directed thrust. This is a converging-diverging, or CD, nozzle. It is a specialized duct that narrows to a bottleneck before expanding, a shape required to accelerate gases to supersonic speeds. High-pressure gas enters the converging section from the combustion chamber at subsonic speeds. As the nozzle narrows, the flow accelerates. It reaches Mach 1, the speed of sound, at the narrowest point, known as the throat. Past the throat, the diverging geometry allows the gas to expand. In a compressible flow, this expansion increases the velocity, pushing the exhaust to supersonic speeds. The acceleration is driven by the pressure gradient between the chamber, labeled PC, and the throat, labeled PT. At the end of the bell, we find the exit pressure, or PE. This value is determined by the specific expansion ratio of the nozzle hardware. Because the metal geometry is fixed, the internal exit pressure remains constant for a given chamber pressure, regardless of the environment outside. This external environment exerts ambient pressure, labeled PA. It represents the weight of the atmosphere pushing against the exhaust flow. While the internal exit pressure is fixed by the nozzle shape, the ambient pressure drops as the rocket gains altitude. This creates a mismatch. The fixed exit pressure rarely equals the continuously shifting ambient pressure. Fluid mechanics requires these pressures to balance at the exit plane. To achieve this, supersonic flow adjusts its wave structure to match the external conditions. At sea level, the surrounding atmosphere is at its highest density. When internal exit pressure is lower than ambient pressure, we get overexpanded flow. High ambient pressure forces exhaust inward, forming oblique shock waves inside the diverging section. With enough pressure difference, flow detaches from interior walls, creating turbulent eddies known as boundary layer separation. Rocket climbs, the atmosphere thins, and the ambient pressure drops. At a specific altitude, decreasing ambient pressure exactly matches internal exit pressure. Internal shock waves and boundary layer separation disappear. The exhaust exits parallel to the walls, flowing in a uniform column, entirely unpinched by external forces. This represents the point of maximum expansion efficiency. By eliminating expansion-related losses, the nozzle directs the highest possible percentage of available energy into axial thrust. As the rocket reaches the upper atmosphere, it nears the vacuum of space. Internal exit pressure is now significantly higher than near-zero ambient pressure. This is underexpanded flow. Gas clears the nozzle and rapidly flares outward through Prandtl-Meyer expansion fans. Downstream, exhaust repeatedly overexpands and recompresses, creating density gradients visible as distinct repeating shock diamonds. Underexpanded flow represents a loss of potential thrust. Much of the gas's energy is spent expanding sideways into space, rather than pushing the rocket forward. By tracking a continuous rocket ascent, we can clearly see the engine's exhaust plume transition through these distinct states. At launch, the high-pressure atmosphere keeps the plume tight and constricted. Mid-flight, the plume straightens into a uniform cylinder as the pressures briefly equalize. In the vacuum of space, the exhaust blooms into a wide cone. Throughout this entire process, the physical geometry of the engine nozzle has remained unchanged. This shift in aerodynamic behavior is a direct result of a fixed engineering design responding to changing altitude. Comparing these states highlights the central challenge of nozzle design. Engineers target a critical mission altitude for peak expansion efficiency.